All right, so we're going to talk about the last experiment of that was done in the early 20th century that sort of was a problem for classical physicists, and that was the hydrogen line spectrum experiment. So what is this experiment? All right, so you take hydrogen gas, okay, and you put it in a tube. Nothing else is in there, no other gases. So first you have to remove all the other gases. So you make a vacuum. Then you put some hydrogen gas into that tube. Okay. And then you're going to put a very high voltage through that tube. Okay. So you're going to apply electricity to the tube. And when you do that, you're going to be exciting the hydrogen gas and it's going to give off light. Okay. Which is a type of energy, right? But the strange thing is that when you do this, you don't get black body radiation at all. You just get certain colors of light given off, okay, and also some invisible light given off. But you don't get a broad spectrum of light like black body radiation, okay. This is at room temperature too, okay. So, for example, in the visible spectrum, you see 4 individual lines of light. You only see 410 nanometer light, 434 nanometer light, 486, and 656. Only those 4 colors, purple, blue, green, and red, are given off. You don't get any orange light, okay? You don't get any yellow light, and you don't get any 400 nanometer light, anything in between. So this was really a problem because what the heck is going on? Why aren't we getting continuous energies of light? If the energy landscape is really continuous, we should. Okay? Well, we now know that quantum mechanics tells us that energy is like a stair, right, and not a ramp, and this ends up explaining all this quite nicely. This experiment is, I think, actually, once you start seeing the equations for this, you'll kind of appreciate why this is, in my view, out of all experiments, the easiest one to sort of see why quantum mechanics is true and classical mechanics is not true, or is not as good of an approximation. Remember, it's always approximations. Okay, so it's not just hydrogen that this happens for, okay? You take any element on the periodic table, and you do the same experiment, okay? You can make it into a gas if it's low enough pressure. So even though magnesium, is shown here, and uranium, those are typically solids, you can get magnesium and uranium gas under low pressure. You will only get certain lines. These are called the line spectra. And these are characteristic of the elements. In fact, back in the day, people knew this for a long time. In the 1800s, people knew this. And in fact, this is how many elements were discovered. Helium was actually discovered this way. Helium means from the sun. And people looked at the line spectrum given off from the sun and saw it had a lot of hydrogen and a lot of helium. That's what's happening inside the sun, right? Hydrogen's going to helium. That's a fusion reaction. But so yeah, a lot of elements were figured out to be new elements because they had different line spectra. They give off different characteristic wavelengths of light, and they don't give off a continuous spectrum of light, okay? And so why is this? It's because electrons are in orbitals and they have different energy levels, okay? So this is the nucleus, and these are different energy levels. And Niels Bohr was the first to try to explain this. He was able to explain this for hydrogen type atoms. And he thought of it as orbits, okay? We now know they're not orbits, but these are just circular orbits. It's like the electrons are planets going around the nucleus, which is like the sun, okay? And what you're doing in this experiment is, in this case, we were talking about emission of light, okay? Because we were exciting it. You are basically ejecting electrons, and electrons are moving from one energy state to another, okay? And that is a change of energy that occurs, and depending upon the difference between, like, let's say this n equals 1 energy level and the n equals 2 energy level, that will give off light with a certain energy, but that energy will be equal to the difference between those energy states, okay? And so this is called the Bohr model of hydrogen. And so Bohr did this for all the different energy levels up to 7. He went further. You can do this for any n, okay? the different orbits. These have different names. I do not want you to know any of these names, okay? But basically, this Balmer series is the one that happened to have where n equals 2, the ground state's n equals 2. You're going from 7, an excited state, to 2, and then emitting light from that delta 5, that change of 5. Those are all those 4 visible ones that I showed you, okay, for hydrogen. So Balmer was the first person to see these with visible light. And then people did experiments in the ultraviolet where you have more energy. That's called the Lyman series. Again, the names don't matter. And then out in the infrared, okay? Still light. It's just some of the light we could see with our eyes. Some of the light we had to see with different instrumentation. It's still fundamentally the same thing. So this is what is happening, guys. You're basically exciting these atoms in our experiment where we're applying electricity to them. And then those electrons are getting excited, and then they're falling back, they're relaxing back to the ground state. And when it's in that relaxation process that they're emitting light. Now, the opposite is also true. You will only absorb certain amount of light. Let's say go from ground state to excited state, or n equals 1 to n equals 2, or let's say n equals 2 to n equals 5. That would be going up to an excited state, right? That would be absorbing light. And you will only absorb light of that correct energy to do that transition, okay? So emission and absorption of light are very similar processes. They're just kind of the opposite, okay? So there's going to be a change in energy based on these different states. And we're going to use Planck's constant and E equals h nu to determine what that energy change is. And Bohr basically figured out exactly what this is. And this was like a Coulomb type interaction. That's why there's some squares in here, okay? But basically, this is a constant called the Rydberg's constant. I'll always give it to you, and I'll give you this formula. It's on your equation sheet. And this allows you to calculate the energy associated with a transition in a hydrogen Bohr atom, okay, using the Bohr model. So it has the final and initial states that the electron is going between, and then this constant, and you'll be able from that to calculate the energy that's either absorbed if you're talking about absorption, or emitted if you're talking about emission. And from that, you can use our other equations that we've learned to calculate, for example, the color of the light, or the wavelength of light, right, or the frequency of light. So that's what we're going to do right now in this problem. What wavelength of light in nanometers would be needed to promote a hydrogen electron from n equals 1 to n equals 3? Okay, so this is an absorption type problem because we're going from 1 to 3. So it's gaining energy. So the hydrogen atom is going to have to accept energy, right? It's going to be absorbing light. And so all you do is you plug this into the equation that we just showed. Your final state was 3 given to us. Your initial state is 1. You get out an answer. This constant, by the way, is in units of joules. Sorry, I didn't show that. That's 10 to the minus 18th. Okay, so it's basically 1 over 3 squared, 1 over 9 minus 1 over 1. That gets you a negative number in here. It's a negative times a negative constant. That gives you a positive number. It's a positive number because the system is gaining energy. It gained light. It's absorption. And then if we wanted to, we could use the formulas that we talked about in the previous videos to convert that energy into nanometers, for example, or into frequency, and we'd find out that this is 102.6 nanometers. So the last thing I just wanted to share with you in this video is that, you know, different types of light have different energies, and this type of light will interact with matter differently. So that previous problem when talking about the Bohr model, we're talking about light of the proper energy, UV and visible, to do electronic transitions, change electrons states, right? Change the energy of electrons. If you have lower energy light, you won't be doing that to molecules, okay, or to atoms. You'll be doing other things. And so you can see here, like infrared light will do vibrations or rotations, okay? And the interaction of light and matter sets up a whole field of analytical chemistry called spectroscopy. I use it all the time in my research, and almost all chemists and other scientists do. But there's all sorts of different types of spectroscopy. Again, interaction of light with matter. And that can tell you a lot of interesting properties about matter, what it's made out of, its reactivity, okay, all sorts of things. So immensely important. We're not really going to talk much about it in this class other than this slide. I just wanted to introduce to you the concept of spectroscopy here really briefly. All right. And then next time we'll continue on and dive a little bit deeper now into the Bohr model of the hydrogen atom.